In the second part of this lecture, we'll create a simulator and we'll illustrate step by step how the recursion is executed in the processor. To create the simulator, we'll need several things. We need for this function, we need the values of A0, T0, the stack pointer, and the return address array. We also need memory. So this is the memory where the stack will be stored. Remember, high address to the top, low address to the bottom. And let's assume that before I call the function factorial, I am at that address on the top. And let's say that the code that calls factorial is at this address that I have right here. This is so in this example, I am writing the value 3 into a 0 and doing a jump and link to the fact function. And the return address for the fact function will be the address 0x00400008, which is the address right below that jump and link instruction. Therefore, the simulator is going to work as follows. The blue line will be the line that just got executed. The red line is the line that I am about to execute. So when I execute the jump and link function, what happens is that the return address is written into array, and I go to execute the first instruction of factorial. The first instruction of factorial will subtract 8 from the stack pointer, so that creates space into the stack, and then I will execute the to store word instruction to save the values of array and A0 into the stack. So if I look, array contains the value 0x00400008, and I'm storing this at the address 4SP, so it will be at the position right above the position indicated for SP. And then I'm storing the value of A, which is 3, at 0SP, so that will be at the position where SP is. So executing those two instructions will change those values in memory. Next, I load the value 1 into T1, which is not shown in the animation. And I ask whether A0 is greater or equal than 1, or so is 3 greater or equal than 1? The answer is no. So I jump to the instruction at the label L1, where I will subtract 1 from A0, so A0 is now 2, and I will execute a function call to factorial. Remember, a jump and link function call, what you're going to do is to write the address right below the instruction, JAL instruction, into array, and jump to that address. So we don't have the address of that instruction in this slide. Let's assume that the address of that instruction is 0x400040. So that takes us to the beginning of the factorial function, where the first thing that we do is to decrement the stack pointer. This way we create space for 2 more words in the stack. We will store the current values of array and A0 into that space. We'll find out that A0 is not greater or equal than 1. That A0 is greater or equal than 1. So we'll go to the L1 at the label again. We'll subtract 1 from A0, so that will give us 1. And now we're going to be jumping and linking to the beginning of factorial again. Therefore, the return address will again be written into array. Even though it's the same, it will be written over. And I'll go to the beginning of the function. We are speeding up the simulation now a bit, so we're going to create the frame for this execution effect, save the value of array and A0 in there. We'll do the test again. The test will again fail. The branch greater than equal be true. I'll jump to the L1, and I'll do another execution of factorial, so it's another jump to the beginning of factorial. I'll create another space in the stack for the saved values for array and A0, and I will write there the current value. So now A0 is equal 0. When A0 is equal 0 and I ask now whether 0 is greater or equal than 1, the answer will be no. Therefore, instead of jumping to the L1, I will execute the instruction immediately below the branch greater than equal instruction. So I execute in the add I instruction and writing 1 into A0. I decrement the value of the stack pointer. Remember that there is no need to restore the values because I did not do anything in this call that changed those values. And then I execute the return statement. The return statement will take me to the current value in array, which is the instruction right below that jump and link instruction. When I get there, I will make a copy of A0 into T0, and I will load the A0 and array back into their value from the stack. So A0 is returned to 1. And array receives the value that was in the stack, that is the 0x00400040, and then I will add 8 to the value of the stack pointer, thus doing what we call an unwinding of the stack. So we say that we wind the stack when we are doing the recursion, and you unwind the stack when we are returning from the recursion. I perform the multiplication, putting the value into A0, and then I return. When I return to the address immediately below that job, that is the 0x00400040. Again, I make a copy of A0. I restore the current values of array and A0 from the stack. So array goes back to 2. A0 goes back to 2. Array is at 0x00400040. I move the stack back up. I perform the multiplication. And I return. My return address is still 0x00400040. So I go back to that position. Again, I will restore, but note that this time when I restore the value of array, the value of array will actually be the value of array or the original call to the function. So the address 0x00400008 is now restored to array. I perform the multiplication, obtaining the final value of the factorial of 3, which is 6. And now when I execute this returning instruction, instead of returning to the middle factorial, I return to the place where factorial had been called. So this simulation, the idea of this simulation is to illustrate to you how a recursion is actually executed. And as you can see, for every time that you do the recursion, you need to allocate another frame into the stack. There are lots of loads and store operations that happen here. Loads and store are expensive operations and should be avoided. So often when I do this demonstration, some students say, so are you telling me that we should never write a recursive function again? And my answer is no. You should write recursive functions because recursive functions are sometimes the best solution for a programming assignment or to solve a problem. And you should rely on your compiler. Your compiler has something called tail recursion elimination. So if you have a tail recursion, your compiler will automatically convert your recursive function into a loop because a loop is much more efficient. However, if you have a problem of performance because of recursive function in some place where performance is really important, you should yourself examine whether the recursive function is the best solution for the problem that you have at hand. But in general, recursion is a very important technique that we have in our toolbox, and we should use it when it saves in terms of programming understanding and expressiveness. There are other data that are stored in the stack. So We have in the stack the saved argument registers, we have the saved return registers, the saved registers, and the local arrays and the structures that we have during the procedure call. And after the procedure call, the stack should always be returned to where it was before we start the execution of the function. So a recap for this part of the lecture is that recursive functions will grow the stack or wind the stack and then unwind the stack during its execution. That is the main message of this lecture.